Now let's figure out where these electrons live and write these electron configurations. All right, so we have some rules. We're going to start with the lowest energy and work our way up. So we'll fill 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then that 3d, then back to 4p, and so on and so forth. Now, we can only put 2 electrons in each orbital. That's called this Pauli exclusion principle. Okay, when we're filling, we're going to fill with 1 electron and then pair when necessary. So let's just look at something like nitrogen. Okay, so nitrogen is in period 2. So we'll have 1s available, we'll have 2s available, and we'll have 1, 2, 3, 2p orbitals available. Okay, so nitrogen is got an atomic number of, anybody know? Think about it for a second. 7. Okay, so that means that a neutral nitrogen atom also has 7 electrons. So we're going to fill the lowest energy first. So we're going to do 1, 2 electrons. Now I do these single-headed arrows. You can draw double-headed arrows. It doesn't really matter. I was always taught that single electrons have a single-headed arrow, and when you're writing these orbital diagrams, it's easier to squish them next to each other when you do these single-headed arrows. Okay, we have opposite spin. Okay, so that's why we have one going up and one going down. That indicates that one is spinning in one direction, the other one's spinning in the other direction. Okay, so we've done 2 electrons. Okay, now we're going to do 3, 4 electrons. Okay, we still have 3 more electrons to go. Now, okay, we're going to do 1 electron and then we'll pair up if necessary. So we have 3 more to do. So I'm going to do 1, 2, 3 like that. And then I can write a configuration, 1s2, 2s2, 2p3. Okay? Now we also know that nitrogen is in 5a, and so it has 5 valence electrons. So I have 2s2, 2p3. What's 2 plus 3? It's 5. There's those valence electrons. Okay? So again, we're going to fill in this order. We're going to go from 1s to 2s to 2p to 3s to 3p to 4s to 3d, 4p, so on and so forth. Now, the periodic table is set up brilliantly for all of this. Okay, so if we look at the periodic table, I add in a line there. Okay, so here I have hydrogen, here I have helium. Okay, then I have lithium, back, beryllium. Okay, and so I'm going to fill that 2s with lithium and beryllium, and then I'm going to come over here and not space this out very well. And I have 6 elements across on there. Okay, and for this we'll get our boron, our carbon, our nitrogen, our oxygen, our fluorine, and our neon. Okay, and so remember, I have S, P. So what's significant here? Well, S, I can only fit 2 electrons, so I'm going to finish up with S like that. Now P, I have 3 different orbitals, so I can fit 6 electrons because I can do 2 electrons in each orbital. Okay, well, let's go. 1, 2, 3, 4, 5, 6. Oh, so that 2p fills across those 6. Okay, now D, let's see how I do spacing this out. Not very well. Whatever. It's just to illustrate this. 1, 2, 3, 4, 5. Okay, so D, I have 1, 2, 3, 4, 5. Okay, so I have 5 different d orbitals. And again, we can fit 2 electrons in each orbital. So if I have 5 orbitals times 2 electrons, that's 10 electrons total. All right, well, what happens here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Look at that. Okay. Now with our f orbitals, now what's interesting is that some periodic tables do this a little bit weird. Okay. Lanthanum and actinum are located in the periodic table in those transition metals. Okay, the lanthanides and actinides should start after lanthanum and after actinum. Some periodic tables put lanthanum and actinum as an additional here. Those don't belong there. They should start after lanthanum and actinum, because if we do that and you count across, you'll get You'll get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 across, because we have 1, 2, 3, 4, 5, 6, 7 f orbitals. Well, if I can fit 2 electrons in each orbital, what's 2 times 7? 14. 14 electrons total. Okay, so the periodic table is structured and set up for all this filling. Okay. All right, well, if we start at the beginning, if we start with hydrogen, hydrogen is our very first element, all right? All right, so we have a 1s orbital. We have a single electron, so hydrogen's electron configuration is just 1s1, okay? Now, on a test or quiz situation that is done on Canvas, all right, the way it will work is if I wanted you to put in hydrogen's electron configuration, what you would see is you would see 3 boxes like this. You would fill all 3 of them. You'd type a 1, you'd type a lowercase s, then you'd type a 1 for that 1s1, okay? So all the boxes end up getting filled, and each box will take one component of it. And I've tried to tell Canvas to superscript because the electron number there is superscripted, all right? So you do need to pay attention to that on Canvas when you do need to fill these in, that you will use each box. You're not going to crunch things together, okay? All right, now let's say I wanted to do helium. Okay, well, helium is still in period 1, so all we have is that 1s orbital. Helium has an atomic number of 2, so I'm going to go 1, 2, and helium would have 1s2. And again, if I wanted you to do helium's electron configuration on a test or a quiz, it would look like that on Canvas, and you type 1, lowercase s, and for this one, it would be a 2. All right, so look out for those boxes. Now, let's stay in period 2. Let's say we wanted to do carbon, okay? So what if I wanted to do carbon? All right, so carbon is in period 2, so we have 1s, we have 2s, and we have 1, 2, 3, 2p, okay? All right, so carbon has an atomic number of 6. So we're going to do 1, 2, 3, 4, and we'd get 5, 6. And we'd write this as 1s2, 2s2, 2p2. Carbon also has 4 valence electrons, and so that's where we get 2 plus 2, 2s, 2p. Those are 4 valence electrons. Okay? So you can see helium, you can see lithium there, and then carbon, which we just did. All right, so what I want you to do is I want you to pause the video, and I want you to try nitrogen through neon before I show you the answers to these. Okay, so this is staying in period 2. Okay? All right, let's see how you did. So nitrogen. All right, we're going to get okay, and then oxygen. Now here's where we'll start pairing up our P's. Because oxygen, we have 4 more electrons to go. So we'll go 1, 2, 3, and there we'll get our first paired P electron. So again, single electrons in each, and then we go back and pair up. Okay, and we'll get a 1s2, 2s2, 2p4. Okay, next up is fluorine. We'll get a 1s2, 2s2, 2p5. Okay, now, in these period 2 elements, what do you notice they all have in common? They all have that filled 1s. Now, if we go back to our helium, they all have the same electron configuration as helium. So I can actually write what's called a shorthand or a noble gas configuration when we have all the electrons contained within a previous noble gas, because each noble gas ends off each period. And so as we go to the next period, as we go to the next energy level, we're going to have every single electron that was contained in the previous noble gas, and we're just going to keep adding to it. So what I can actually do is I could write this as helium 2s2, 2p5. I can write this as helium 2s2, 2p4. I can write this as helium 2s2, 2p3. Okay, so let's say I gave you a test or a quiz and I said I wanted you to write the noble gas configuration or the shorthand electron configuration. What you would get is you'd get a box for the brackets. We're going to do fluorine. Then you'd get a box that looks like this, like this, like this, like this, like this. And so I would write fluorine by typing the noble gas in one box, and my 2, my S, my 2, my 2, my P, my 5. Okay? So if I ask you for the shorthand electron configuration on a test or a quiz on Canvas, that's the way it'll look. Okay? So you'll put the noble gas in brackets in one box, and then you'll fill the other boxes like I showed you before. All right, and then we ran out of room, so here's neon. Now we're still relatively early on this, so writing a complete electron configuration is not so bad, but as we start getting further down, they get longer and longer and longer and longer. And so it's actually really nice to be able to write those shorthand ones. Now, what do you notice about neon though? Do I have space for any other electrons in neon? I don't. So neon, coincidentally enough, ends off period 2. And so now that's full. And so when we get to period 3, we're going to have all the electrons contained in neon, and then we're going to keep adding. Okay, so there's our period 2 configurations, and you can see I've got the electron configuration, so this is the complete. And this abbreviated, we also call that the shorthand. Okay? All right, now, when we get to period 3, okay, so here's phosphorus. So period 3, if I were to fill everything in for phosphorus, we would get 1s2, 2s2, 2p6, which again is the electron configuration for neon, 3s2, 3p3. So I can also write that shorthand. Because here, that's neon. Okay? And so we call those the inner electrons. And then everything that comes after the inner electrons is now our valence electrons or our outer electrons. And it's our valence electrons that are involved mostly with our bonding. Okay? So we can do the same thing we did before. We can write out all of these configurations. We're going to do partial, and we're going to write the shorthand. Okay, because now these are getting really long, because I'll show you. I'm going to do sodium. I'll do the complete one first. 1s, 2s, 2p. Going too fast. Okay, so sodium, we'd get all that. So the complete would be that 1s2, 2s2, 2p6, 3s1. So it gets really, really long. So what's better is to go ahead and write our neon. And now I'm going to do 3s, 3p. I'll get that. And I'll write that. Okay? So I can do the same thing for magnesium. We've got 2 valence electrons there because magnesium is the second element there in period 3. So we'll get, okay. And if I wanted to do aluminum and chlorine. So pause. I want you to try aluminum and chlorine before I do them. All right, let's see how you did. Oh, okay. Well, that was interesting. It jumped slides, but there's your aluminum and there's your chlorine. So yours should look somewhat like that. So aluminum, you've got a neon with a 3s2 and a 3p1. Chlorine, you have neon with a 3s2 and a 3p5. And then we get to argon. And if we look at argon here, do we have room for anything else? We do not. So now when we go to period 4, now we can have argon as our noble gas. Okay, so when I look at arsenic, okay, arsenic over here, all right, so we've got, let's see here, I'll do it down here. We've got argon. Now we have our 4s. Now remember, it goes 4s, then 3d. And we have 1, 2, 3, 4, 5, 3d. 1, 2, 3, 4p. Okay, and so we're going to fill all these. And then, all right, so we'll get our argon. I'll write it over here. Okay, now what's interesting is the s and the p electrons are considered the valence electrons. So 4s2, 4p3, 2 plus 3 gives me 5, and so arsenic is indeed over here in group 5a with 5 valence electrons. Arsenic's a main group, so those 5 valence electrons are the valence electrons. In the transition metals with the d electrons, we're going to see that most of them have very similar s configurations, but as we've learned, we can get variable charges on our transition metals. I can have a +1 or a +2 or a +3 or a +4, etc. What happens is once we mess with the s electrons, then we can start messing with the d electrons. All right, so let's take a look at some period 4. All right, now I'm not actually going to write out all of these. So what I have on Canvas is I have a handout that has electron configurations for everything through the end of period 4 that I want you to download, practice filling out, and then check your answers. Both the handout and the answer key are posted on Canvas for you. Okay, I'm going to do 2 of these period 4 configurations for you. I'm going to do chromium and I'm going to do copper because chromium and copper are exceptions to the rule. So chromium, okay, so the chromium expected for S 3D. Okay, so our expected would be this. Okay. Now, what we have found experimentally when we have looked at chromium is that this is not what we see. Okay, chromium, for what we understand about the stability of everything, is it actually is less stable to have a paired up 4s shell there and to have an empty 3D orbital. So this is not what we see. So chromium actual. Is we see this. Okay, so this is the actual for chromium. So we're going to get an argon 4s1 3d5. Okay. Now copper is very similar. Okay, so copper expected would be this. Okay, so we'd expect, okay, similar to what happens with chromium. Okay, this is not what we see. The actual is it is more energetically favorable to have an unpaired 4s electron than to have that unpaired 3d electron. So this is what we see. Okay. The rest of the elements in period 4 will follow the expected. Okay, you'll just keep adding an electron as you go through. It's just chromium and copper we see these two exceptions to. Okay, for this course, the handout goes through period 4. For this course, you are responsible for knowing how to write electron configurations through period 4. Okay, I'm not going to make you do anything beyond that. Once we get into period 5, we start seeing more exceptions. And then once we start getting into our lanthanides and our actinides with the f orbitals, things get way more complicated and we start to see even more exceptions. So you do need to know chromium and copper. Okay, you do need to know that those are exceptions to the rule, and what we actually see is a little bit different. And then everything else in periods 1 through 4 are going to follow what you would expect to see as you build up the electron configuration. So you are responsible through period 4, including chromium and copper. Okay? And then here you can see these valence shell configurations for the entire periodic table. And you can start to see where in period 5, we start to see some different exceptions. Now this chart is interesting. This is showing the d electrons before the s electrons. That's not the right way to write it. You're going to write them the way I did. You're going to write them in the order with which they fill. You're going to write s, then d, then p. Okay? S, then D, then P. There are some books and some YouTubers I know that do the D electrons first. With this course, that is incorrect. Make sure you're writing your S electrons before your D electrons. All right, and so those are our electron configurations.